Okay, so the following discussion is proof that relational database systems are great hosts to also non-relational data. Database systems or relational database systems are purposely built to hold rectangular grids of data, and that's what they're experts in. But this doesn't mean that we can have other data models properly represented and properly encoded inside the relational database system, so that other data models, in this case JSON, will also be available for relational operations and can coexist with other tabular data. So in fact, PostgreSQL can make for a quite decent JSON storage and JSON query processor, as we will now see in the following minutes. If you don't know about JSON, JSON is a data format that has its root in the JavaScript language, in the JavaScript programming language, where you have a particular syntactic notation for JavaScript objects. Derived from that is the JSON, the JavaScript object notation, that is now used completely decoupled from the JavaScript language and is used to represent structured values and communicate such structured values between applications of all kinds. JSON is the primary data exchange format on the modern web, I would say. It's used virtually anywhere. JSON instances of data are found everywhere, and it's of great use to be able to ingest these, to import these into relational systems and then operate on such data, or to generate JSON data from relational tabular data, export this JSON notation to have the database system play the role as a JSON data provider, as a JSON source for other applications, for the web, for example. All right, so a very brief review of what JSON actually means. So this is a very minimal grammar, an excerpt of the true JSON grammar, which is in fact, the true JSON grammar is in fact not much larger. JSON really shines when it comes to a very compact, very regular and simple description of structured data. So in this grammar, let's start at the very bottom here, at the value production. So a JSON value can be a string or a number, a string in double quotes and a number in the usual syntax that you would probably expect. JSON values can also be the two booleans true and false, or this relative of a concept that we know from the relational database system. A JSON value can be null. But it gets more interesting when JSON values represent collection of things. So for example, there's the possibility to specify array values in JSON, and they are specified, as you probably would expect, in square brackets. Elements of an array would be considered and specified in square brackets. If there are any elements, arrays can also be empty. If there are elements, they are comma separated values, and values can be simple values like string and numbers, but they could be arrays again. So JSON allows for some arbitrary nesting of data, which is quite the opposite to the flat 1NF relational data model. All right, so one way to represent nested data properly could be to have it in JSON format. We will look at other representations of nesting in tables, but JSON would be one option maybe. Okay, the main construct in the JSON notation would probably be the object. An object is just a comma-separated list of fields or members as they are called. Okay. Each of such a member is a pair consisting of a field name, specified as a string, and a value again. So there's some nesting and recursion going on here again. Multiple such field value pairs are separated by commata, and an object may even be empty. And that's about it. That's all about JSON syntax. So it's a very regular, very flexible, very simple syntax that allows to construct really complex nested structures. Okay, we can hold such structures inside single table cells inside our relational database system. Since SQL 2016, there is a very well-defined SQL to JSON and JSON to SQL interoperability defined for SQL database systems. Since then, database systems can be very welcoming hosts to JSON data. And although the data that we are putting in such a table cell can then be very deeply and very richly structured, we would still consider this to not violate the first normal form. From the viewpoint of the relational data model, the relational algebra, the purest view of the data, such a JSON cell has no interesting relational structure. It cannot be investigated using projection or selection operations of the relational algebra. From the viewpoint of the relational data model, a JSON value is a black box. We will of course see that PostgreSQL comes with particular operations that can inspect these black boxes and look inside such JSON values, but these would be JSON specific operations, not relational operations. All right, so let's see how some sample JSON objects on values might look like. So this would be a JSON object enclosed in curly braces with two field value pairs. Okay, so this would be such a pair with field name episode and value 8. This is another pair, field name title with a string value, The Last Jedi. All right, so this could be a very simple representation of one of the Skywalker saga films. Okay, an object with two members. This would be an array with 5 elements. All right, an array with 5 elements. Arrays are enclosed in square brackets, as you can see. And the 5 elements of that array are objects again. And nesting and recursion is going on, as you can see. And as you can see, the objects, the field in these objects, each object carries 4 fields, A, B, C, D, are really regular. So such an array of objects appears to represent the same information that a relational table could represent. And indeed, this 5-element array of JSON objects is just modeled after the table T that we've used so many times already in this lecture. So the information content of table T and this JSON array of 5 objects could be considered the same. Okay. So how would one construct such JSON values inside SQL queries? And there is no surprise here. We will of course use the literal embedding, the textual embedding of JSON values into our SQL queries. We can use literal string syntax and then cast these strings to a JSON data type, the JSON data type inside PostgreSQL. Actually, PostgreSQL comes with 2 JSON data types, and I'll be highlighting the difference between the two in a minute. But in the course of this example and our discussion of this video, but also of the entire course, we will probably only work with this particular JSON data type, the JSONb or JSON binary data type. I will come back to the differences to the other JSON data type in a minute. All right, so we will just use literal embedded strings. This would be a JSON object embedded in single quotes, and inside these single quotes we expect valid JSON syntax. 2 field object with fields A and B and values 2 and 1. All right, so this would be a valid JSON object. There is 2 fields A here, and the internal representation of your JSON objects would have to take care which of these 2 A fields would persevere. All right, and this would be array syntax. This would be just array syntax. You see that I've specified the 3 array elements, 0, false, null, inside this one array. Okay, casting these literal embedded strings to JSONb values will of course initiate JSON parsing and will complain and reject syntactically malformed JSON values here at this point, as you can imagine. For this example, everything goes fine, and that would be the resulting table. So this column 2 would be of type JSONb. Okay, and this means we could apply further JSON specific operations to these values in column 2. Okay, so maybe you wonder why we have to use the the casting here in the first row of our literal table, but don't use casting in the following rows. Well, this is a fact that the first row in such a literal table determines the number of fields and determines the field types for the entire literal table. So after we've passed the first row, it's clear that the second, third, and any further row will have to carry JSONb values in the second column, and casting will be implicit. Okay, so that would be one way to generate literal JSON values inside SQL scripts. Once we have JSON objects, we could perform query operations on them. And the most basic, the most fundamental query operation on the JSON value, because JSON values can be deeply structured, would be to reach inside that structure, and extract single fields of an object or single elements of an array. This is what the access notation is being used for. And you see that it comes in some infix arrow notation inside PostgreSQL. So if we are facing an object that has particular fields f, then the right-hand side operator of these arrow notations would be field names f. So if we are accessing elements of an array, then the right-hand side argument of these arrow notations would be numeric array indexes, which allow us to look inside at particular positions in an array, in a JSON array. JSON arrays are indexed starting with 0, by the way. Okay, so this would be one possibility to reach inside a JSON value and access a particular field, extract a particular value of field f, or access the element at position I. Okay, you see that we are using this one headed arrow here in this part, in these first two lines, and the convention inside PostgreSQL is if you access a field or an element using this one-headed arrow, then the result of the access will be a JSONb value again. Okay, so extracting parts of a JSONb value will yield a simpler constituent JSONb value, to which, of course, I could apply further access operations. So I could then navigate further and deeper into the nested structure of the JSON object. If I'm using this double-headed arrow here, then the extracted value will be converted to text automatically. All right, so extracting field values or extracting elements at a particular index inside an array using the double-headed arrow will yield a text value. A text value cannot be subject to further navigation using this arrow syntax, for example. But a text value would be perfectly suited to be converted, to be casted into, say, a number or a Boolean or a date value or what have you. So that would be the bridge between the extracted value, JSON values, and the rest of the PostgreSQL type system that would allow me to then further process the extracted values and apply the operations of the target type that we've casted to. Okay, so two different use cases. Extract JSONb components, extract values that are then casted to text. All right. As I've already mentioned, such navigation inside the deeply structured JSON value might contain multiple of these access steps. And to save you from specifying such long access chains, there's a shorthand notation inside PostgreSQL which lets you apply a whole path, a whole sequence of such field and field accesses or element accesses to one particular JSON value. So this would be a field or element access, and the result of that would be fed into the next field or element access and the next until we apply the last navigation step. And the last navigation step will be a JSONb value unless we use this particular variant of the path navigation operator where the result will be cast into a text value prepared for casting. So let's see how this looks like inside PostgreSQL. So this is the literal table of 3 JSON values that I've shown you earlier on the slide. And you see that I've decided to cast all of these embedded literals here to JSONb values, to the JSON binary variant of Postgres internal JSON representation. So let's try that. This is what comes out of this. It's a 3-row table with first column carrying the 1, 2, 3 values. That's fine. And column 2 carries JSONb values. Okay, you see that I've specified the fields of an object in this particular order, and that in the internal representation as a JSONb object, Postgres has decided to switch the order, which is okay, because there is no interesting or well-defined order on the fields of an object. Of course, it's different for arrays. The order of array elements is, of course, important and vital, and the internal representation, the JSONb representation of Postgres, of course, preserves the order of array elements. Okay, what is not preserved, as you can see, is some excessive white space that I had included in the specification of my arrays. This is thrown away and normalized after the JSONb internal representation has been created. So any excess white space and so on is being removed. And you can see that there are also rules applied that concern the non-unique field names. So you see that the last mention of the A field name here in this object takes priority and has been included in the final JSONb value. In the JSONb value, field names have to be unique, which makes sense for JSON objects. So that would be the JSONb variant of things. As you can already see, there's also a JSON variant of things. So this is just the JSON data type, not the JSON binary, but the JSON data type. And so let's see what comes out of that. Okay, looks similar to me, but it's not the same. As you can see, casting to JSON preserves the order of fields inside such an object. Okay, it even preserves the non-unique field names, which is questionable in some scenarios. So this is being preserved. It even preserves white space. And when you see that, so here are the 3 accepted white space. When you see that, you probably understand what happens internally. Internally, the JSON, not JSONb, the JSON data type really stores the literal textual notation of the JSON objects. The JSON objects are copied literally and held in this particular textual format, so that all white space, oddities, and so on are preserved. This also means that with any access, with any operation on such JSON values, we have to repass the internal string representation again and again. So white space is preserved, and that can be really crucial for some applications. But if you really look at JSON as a data format that represents restructured values, then white space is probably less important to you. And then the JSONb variant of things might be more efficient. Excessive white space is removed. Parsing and validation of such a JSON value is performed once and then held in an internal representation that is more efficiently accessed later on. Okay, so one final example would be the access to such structured JSON object. You see that I have constructed a nested JSON object here. All right, a JSONb object in this sense. Okay, so the internal representation would be constructed once and is then ready for navigation. Okay, so this is what we have constructed, and the navigation leads us to the field B of that constructed object. Okay, so the field B of the constructed object will be extracted. This is the field B. The value behind that, this object, would be extracted. And because we are using the one-headed arrow, the constructed value, the value of this sub-expression, would again be a JSONb value. JSONb values are subject to navigation, for example. For example, by this two-headed arrow. So inside this extracted sub-object, I would then access the B2 field. This is the B2 field. And I would extract this value 2 here. And I will make sure that it's not extracted as a JSONb value, but it's extracted as a textual value. Just a string containing the character 2. This is subject to casting to int, for example. I could not cast a JSONb value, but I can perfectly fine cast a text value to int. So after this cast, I will hold an integer 2 in my hands, to which I can then do further operations, for example, the addition of 40. And this should yield 42 if everything goes well. There you go. All right. So that's the construction and the navigation of JSON values. But there is a bit more to JSON support in PostgreSQL. We have very expressive and very convenient bridges between the world of JSON and SQL. Given JSON objects that you are holding inside your tables, it would be nice if you could make use of the very extensive SQL support, the query support inside the relational database system to process the components of arrays and the components of JSON objects that we have stored in our system. And there is a whole family of functions that allow us to go the way from JSON values into a relational representation that we then can manipulate using select from where or just SQL, syntax SQL operations, and the other way around, to go from SQL or relational values to the world of JSON. So convert entire tables or maybe even only a single row into a JSON representation, which can then be externalized and maybe sent outside the database system to be processed by some JavaScript-based application, for example. Okay, so let's see how this works. The bridge between JSON and SQL. All right, so first, let's go the way from JSON to SQL. The way from JSON to SQL. So what we are given would be a JSON object like this one with n fields, or a JSON array like this one with n elements. Okay, and the JSON to SQL bridge inside PostgreSQL would convert such JSON values into tables, which are then subject to further querying. JSONb each of object O would yield this two-column table in which the key or the field names and the values stored in these fields would be held in separate columns and in n separate rows. And of course, we could use this table in further SQL query operations to explore which fields, which keys the particular object O had and which values were stored inside there. So that would be one way to go from the JSON to the SQL world. And as the footnote already says, there is more than one way to do that. And I've brought an example with me in which we will explore other ways to convert JSON objects into relational structures, tables or rows, for example. Something very similar is possible with the JSON array A that we have defined here. We could just use the JSONb array elements function and expose all the n array elements inside that JSON array. We would obtain a single column table that just lists the n values that were formerly stored inside the JSON array. So this would be a column of JSONb values, of n JSONb values that have been extracted. Now, an array inside the JSON world, actually any array outside there, has an intrinsic order, an array element order. So this would be the first array element, and this would be the last array element. Order is lost in this relational representation. Please don't be fooled by the fact that v1 is listed first and vn is listed last here. You know that there is no defined order on a relational table, and this is just a relational table of JSONB objects. Okay, there's a variant of the JSONB array elements function that can also incorporate the order of the elements and make the order of the extracted elements explicit. I can only encourage you to look up the PostgreSQL documentation of JSONB array elements to find the annotation that you have to use to this particular function to also expose the array element order. And what you will get is a 2-column table in which one column represents the order. Okay, if you don't find the material inside the documentation, look for with ordinality. I'm not showing that here because we will use with ordinality plenty of times in the sequel of the course. Okay. So how about the other direction? How about following the bridge from SQL to JSON? So you are given SQL data, like a record, or a row, or an entire table. How would you transform such values into JSON values? And again, there is multiple answers to this question. There is the row to JSON function, which really already in its name carries everything you need to know. A single row, the argument of this function, a single SQL row can be converted into a JSON object. And the field names of the row, as you might have guessed, will end up to be the field names of the JSON objects. The column entries of the row will be the appropriate field values of the constructed JSON object. And that's what we're doing here. We are iterating over all the rows of our playground table. And as you recall, the rows of the playground table carry 4 fields, A, B, C, D. Okay, so the constructed JSONB object here will also have those 4 fields. Okay, so this will be a table of 5 JSONB objects, all of which carry A, B, C, D field names constructed from this simple query. Okay, so when it's our plan to not generate okay, so a second possibility would be to convert this table T, the table T, into a single JSONB value, not into 5 individual JSONB objects, but into a single JSONB value, in this case an array of JSONB objects. How to obtain the individual objects we have just seen? We would just use row to JSON. And then we would use an aggregation function, a particular aggregation function that would collect all these 5 rows and would construct a single value from that. That's just the role of aggregation functions. And in this case, we would construct an array of such objects. We will come back to this array ag function, which will become one of our best friends in the next chapter of this course. For now, just note that the array ag function is an aggregate function that will collect all of its arguments, in this case JSONB object, into a SQL array, and we will then convert the SQL array into a JSON array. Okay, so for now, just view these two functions like construct the array and then immediately after that convert this SQL array into a JSON array. Consider these two functions to be a unity for now, but we will look closer at array processing in the next chapter of the course. So this simple query, it's still a 2-liner query, would convert the entire contents of table T into a single array value, JSONB array value, in which inside we will find JSONB array objects. And the entire information content of T ends up in a single JSONB value. Okay, so I think it's time again to switch over to the editor and see how this works in practice. All right, so this is our playground table T, and we could just convert its contents into individual JSONb objects. So that would yield another table, a 5-row table in which each of the rows we'll find an individual JSONb object. Let's see. There you go. 5-row table, 5 individual JSONb objects with fields A, B, C, D as prescribed by the schema of table T, or the type of the row variable T, you could say. This would be the version in which we aggregate everything into a single JSON array. And we would use the composition of these two functions, which first construct a SQL array and then convert the SQL array into a JSON array. Okay, so let's see what happens. Whoop, okay, so we end up with one row as expected because we were aggregating the individual JSONb objects into a single JSON array. This is the single JSON array. You see the leading and the closing square brackets here. This indicates that we've indeed constructed such a JSON array. It's really ugly to read, and the output is really hard to digest. So there is another built-in function inside PostgreSQL called the JSONb pretty function, and it does just what you are expecting. It will prettify the output of any JSONb value. So let's just do that and then check again that we have constructed the right thing here. Yes, this is a JSON array, and it now the table now contains a prettified, a stringified version of our constructed JSON object. But we are confident now that the entire contents of table T has been properly converted into a JSON array. So what we could do now is to take that table T and apply to it this row to JSON object and then JSON objects to single JSON array conversion, and store what we have achieved so far. So let's store what we have achieved so far. What we end up with is the table that is almost like T. It only has a single row and a single column, and inside that single cell we'll find a complex JSONb array with JSONb objects as elements, and the information content of this table would be just like T, but in JSON representation. So let's create that table, and it's properly named like T but as JSON. All right, like T but as JSON. You see that I'm using the temporary modifier here because we are just playing around. When I end this session, the like T but as JSON table will be gone again. Okay. Yeah, we could look at this, but we have seen it already. This is a single row, single column table that contains the entire contents of the original playground table T. Okay, so this was the trip from relational data to a JSON representation. Can we now get back from this JSON representation to the original table again? Can we do the full round trip? Then we would be sure that there really is the interchange between relational model and the JSON data model is really something that is workable, that is really practical. So let's do that as the final step of this demo. Let's get back from this table that is like T but is JSON to the original T table again. Okay, so the first step, because our table like T contains a JSONb array, would be to access the individual array elements again. Okay, and we have seen that particular built-in function on the slide already. It's the JSONb array elements function. What I get back here is a virtual table, is bindings for all the different array elements that I can extract here. Okay, and I'm calling these extracted objects. I call them objects, or I call them O here with aliasing. So let's see what I get. Okay, All right, so the JSONb array has already been dissected into 5 individual elements, in which in this particular case are 5 JSONb objects again. Okay, so that would be the first step. All right, what we could then do to each of these objects, we could apply the JSONb_each function. The JSONb_each function, if you recall from the slide, would process such a JSONb object and separate it into individual fields and return a 2-column table in which the first column would hold the key or the field name and the second column would hold the JSONb value stored under this particular field. So that is something that we could do. Let's see what the result would be like. Yes, that's the result. So we've seen that there is an A1 value and an A2, A3, A4, A5 value stored in these JSON objects, and we indeed find all of these A1, A2. We find all of these here in the relational representation. This is one possible way to do it, but in this relational representation, the information of which fields were actually making up one JSONb object, this is gone. Okay, so we know from recalling the original JSONb input that this have been the fields of one particular JSONb object, but this is not encoded in this relational representation. Sometimes this conversion into a relational value is enough, but normally we would like to preserve the JSONb objects. We would like to convert the JSONb object into a single row. Okay, and we can indeed do that. We would start out again and would dissect the JSONb array of objects O, and each such object O I would subject to the built-in function JSONb_toRecord of O. And you can already tell what JSONb_toRecord will be doing for us. It will convert the object into a row, into a SQL row, whose fields are the same as those the JSONb object O. Okay. We have to be very explicit. We have to be very explicit in to which types, to which SQL types we want the JSONb values of object O to be casted. So we know that the JSONb value under field name A is supposed to be an integer, and that's what we are specifying here. And the implicit casting of PostgreSQL will apply casting to the extracted one value and yield an integer value. It will apply casting to this extracted JSONb value and it will yield a text value. It will apply Boolean casting, and again it will apply integer casting, thanks to the specification of the row alias or the row types that we have appended here. This is very important. Otherwise, SQL is not clear to which types you want the different JSONb field values to be casted. Now this is very clear. It will be int text boolean int. All right, and we can do that. And if we execute this query, then we get back our original table T again. Okay, so we went from T to the JSON representation in the table like T but JSON, and we now went back to the original representation of the table T again. Nothing has been lost. So these two data models can really act as two alternative representations of the same pieces of data. There is a variant of the JSONb_toRecord function. If this is strange to you, then there is a variant of the JSONb_toRecord function that's called JSONb_populate_record. And the JSONb_populate_record still accepts the object O as one argument. The object is to be converted into row, and the row type that we are expecting, the row type to which we want to convert the fields of our object O, is simply given using this dummy value here. So the null value is completely arbitrary. We could any row value of type T would be okay here, but null is particularly convenient to denote here. This is the important bit. This is the important bit. This is the information that PostgreSQL needs to know how the different fields of the objects O are to be casted into SQL types. All of this is encoded inside the SQL type, and this is just the SQL somewhat peculiar way to communicate the row type T to the JSONb populate record function. Okay, this is an alternative way to do it, and we obtain the same original T contents again. So this would be an idiom, I would say. First, explode the array element into individual elements, and if these are JSONb objects, then inspect these and use these to populate individual records from the object fields. Okay, because this is so commonplace and such a widely used idiom, there is even a built-in function inside the JSON library inside PostgreSQL, which will do both steps, array explosion and field conversion for the objects in one go. It's the JSONb populate record set function, which accepts an entire table in which it expects to find an array of JSON objects. Okay, and the elements will be exploded, the objects converted according to the row type T. We have just seen the trick a few lines above, and then we will end up with the expected table that carries the same information content as the array of JSON objects. There we go. Okay, so much for JSON. A very rich data representation format, which suitable bridges that bring us from SQL to JSON and from JSON back to SQL. And this idiom of going from the relational data model to some alien data model that lives inside your database system and then going back from that alien data model back to the relational world is something that will recur in our discussion of advanced SQL. This idiom is also being used to process the values of a data type that is really very similar to JSON. It's the extensible markup language, or the XML format, in which we use textual representations like this to specify ordered trees of nodes, ordered trees of data nodes. So you can see that this outer tag here represents the root node of a tree-shaped hierarchy of nodes, the movie node. Inside this outer root node, we have two further nodes nested, the release and the title node. You can find this here in this tree depiction of the XML value. Inside the release node, you'll find not another node, or well, it's a text node, as the XML folks would say. This is a leaf node inside our XML representation. No further other nodes are nested inside it. It's just textual leaf information, and you will find that here in the tree representation. All right, the same is true for the last Jedi here. This is just leaf content, textual content inside the XML document, and you can find that here. You see that the title node is further specified by this episode attribute, as it's called in the XML speak, and we could also find a place for that in the textual tree representation of this tiny XML document. Okay, so this is what XML provides you with. It's a textual representation of ordered trees of textual information that lives in the leaves of these ordered trees. Okay, I think everybody out there has already seen either XML instances or maybe HTML5 documents, which are also instances of the XML language. This is an extensible markup language that can not only speak about movies, but also about HTML5 documents or about any data format you can envision at all. All right. XML support inside SQL system even predates JSON support. XML is a very old idea, and SQL systems have facilities to ingest XML data, convert it into an internal XML representation, and then also convert that XML representation into relational values, for example. So there is bridges built in from XML to SQL and from SQL to XML. And the whole story, the JSONb or the JSON story, would repeat at this particular point. I will not further discuss this here. If you have understand the gist of the JSONb or the JSON to SQL bridge, then you understand the rationale and the philosophy behind the XML bridge inside relational database systems. So let's not go deeper into this here. There's even an entire course that I've prepared on how database systems can interact with XML documents and how database systems can actually act as very efficient processors, query engines for XML data, even if this XML data is of the size of multi-megabytes or gigabytes. But really, this is a story for a different course, not this course. This is Advanced SQL, and it's going to stay Advanced SQL. Until then, see you and take care.